So I'm just wanting to basically review multiple regression a little bit before we finish up on effect sizes of multiple regression. So just a reminder again that multiple regression, we have a single dependent variable that is continuous. So that's one of our first big assumptions, that there has to be an outcome, a dependent variable, and that variable does need to be continuous. However, beyond that, what defines a multiple regression from simple regression is that we have more than one predictor or independent variable. So two or more predictors. And those predictors can again include a lot more than we normally would be talking about within a simple regression. Obviously, we can put single predictors in as linear trends, and this is the assumption that a multiple regression will make unless we give it information to know otherwise. In other words, if we're simply putting in a variable, multiple regression, if we have not adjusted that variable or created that variable, is assuming that it is looking for a linear trend. As we discussed, we can put variables in that we're not actually interested in as predictors in a hierarchical regression, where we're putting them in a block to basically remove their variance to begin with. So the question, for example, we could put our covariates in first and say these are things that we think are going to be related to the outcome, and we're going to let them occupy or claim that explained variance that they explain in that outcome in our first block, to then ask the question, do the predictors that we're interested in still have a relationship once we remove those covariates? Usually if we're doing covariate analysis like this, the whole purpose of it, the reason that we would be doing it, is that we're actually wanting to find out if there is effects occurring after we've adjusted for noise or chaos or confounds. So remember, a confound is a variable that co-varies with our outcome that may impact the outcome of a study or a hypothesis. So one of the reasons we use true experiments is to try to remove confounds from ever existing. But a lot of times in applied research, we don't actually have the ability to do a true experiment where we're controlling all possible elements other than the one thing we're wanting to change. So there's very likely going to be confounds. If we can identify and measure those confounds, we can put them into the equation in a hierarchical regression in that first block and eliminate their actual effect on the outcome by accounting for it. We talked about that for the most part our predictors will typically be continuous, but multiple regression allows us to also use categorical variables. So normally the only type of categorical variable we can use in a correlation or simple regression is a dichotomous categorical variable. Dichotomous meaning two levels. However, because multiple regression allows us to use multiple predictors, we can actually take a categorical variable with three or more levels and through dummy coding use it as well. And that's what dummy coding basically means, is we're actually going to create a new series of variables to represent that original one categorical variable. So if it was a three-level categorical variable, so the initial column in SPSS was coded 1, 2, and 3, we would recode two new columns. The first one would be basically the presence of 1, whatever that represents, and all other codes, the 2s and the 3s, would become 0s. The second column we would create, now 2s equal 1, and 1s and 3s equal 0. Because we've now created two columns, those two columns represent the three possibilities. So if we put them into the equation, we can now put them together in a block. So again, this is hierarchical regression. And then by looking at that block, we're going to get information about how each categorical variable is related to the outcome. Because we're going to have a column which represents the presence of the first categorical option, a column that represents the second categorical option, and then if neither of those are present, that by de facto or default represents the third available option. We can also create nonlinear trends, and again the idea behind this is we're simply taking the original continuous variable and we're not multiplying it, we're bringing it up to a power of. So for example, we're multiplying it by itself, we're squaring it to create a quadratic trend. Basically the idea that there is a bend in the data, that it starts possibly as a positive relationship but at some point becomes a negative relationship, or starts as a negative relationship and eventually becomes a positive. As we raise the power that we're bringing that original variable to, as we create a column variable, to the third power or fourth power, we're basically, every additional power is telling it to look for one additional bend in the data. And finally, we can take two continuous variables that already exist in SPSS, two columns, and multiply them by each other. So basically, predictor 1 multiplied by predictor 2 to create a new column, which is the interaction terms. So that's the basic concept of what we can do with multiple regression. So looking at SPSS, the regression coefficients are what we're actually interested in. So those are the information that we're looking at. The interpretation of regression coefficients does depend on the purpose of the additional variables. So we can have several predictors in a block. So for example, in this case, we have a couple of models that we're looking at. The first model only had a single predictor in it, anxiety. The second model has a constant, anxiety, and sex. So we've added an additional variable. So the constant is the same in both cases. We have a constant, and that constant again represents what would happen if the predictor or predictors were all set to 0. Notice the constant in the model with only one predictor is a 3.914. So that's the start point of our regression equation. However, the constant in the model 2, where we have two predictors, it's lower. That's because, again, that's the constant it would be if both of those variables in the model. Following by the constant is now the slope. So again, notice that anxiety in the model where anxiety is left alone to predict our outcome has a slope or a B weight of 0.248. So for every unit of anxiety, we're seeing an increase of 0.248 in the outcome variable. In this case, the dependent variable in this data set is hours, probably hours of studying, I'm not exactly sure. Doesn't really matter, we're just looking at the data here at this point. Again, notice it does change slightly when we add sex. So anxiety is now a 0.244. That probably represents that anxiety and sex, and in this case most likely gender, is somewhat slightly related. So when we add sex or gender to this model of prediction, it takes a little bit of that variance that was explained by anxiety and is now assigning it to sex. Now finally, once we actually have our model and we know that it's significant, we do need to interpret how significant those individual predictors are. So again, if we look at the two tables, Model 1 and Model 2, in Model 1, you'll see anxiety has a t-value of 3.748 with a significance of 0.001, and a very similar value at the bottom. Again, in Model 2, it's now a t of 3.915 and a significance of 0.001. And that gender also has a t of 2.146, and again, its significance is 0.041. Again, below that 0.05, both of these are significant predictors. As far as our degrees of freedom, again, the degrees of freedom for reporting this information is the number of participants we had minus the number of predictors minus 1. So just a reminder, multiclinearity, independent variables, basically this represents when independent variables are too related to each other that they basically are causing a problem within the equations of prediction. It's basically the idea that if you have two independent variables that are correlated at R of 0.90 or higher, which is one of our kind of rules of thumb of identifying multiclinearity, you've probably got two separate measures that are measuring either very similar constructs or possibly even the same constructs. And like I said, the problem with this is that all statistics are making estimates of error, and they're assigning error to various variables. They're assigning that variance. And when we have two predictors in a multiple regression model that are highly related to each other, often what happens is that that adjustment or that assignment of both variance and error becomes very unstable. And we can get very different results just depending on what particular method we can use. And we talked about how stepwise, forward, inter, and hierarchical will give us different results. And it's true, they will. But what happens with multiclinearity is that it's unpredictable how that's going to happen. In the other cases, we kind of can guess how it's going to happen. So if I put in one particular variable first, I'm expecting that it will be grabbing up most of the variance compared to what I might follow up with a second or third or fourth variable in forward regression, or if I've assigned them in a hierarchical. If I actually have multiclinearity, that is no longer necessarily predictable because the regression model is going to struggle to figure out how to put these two highly related predictors into a model. So again, just a brief review of what we can do with regression. Again, the inter method is when we have no theory, we're just letting statistics decide, and it's deciding what order to put the predictors in based on how much uniquely explained variance each predictor is predicting. So it's pretty much ignoring any shared variance between the predictors to then ask, once we remove the estimates of error, once we remove any shared variance, which particular predictor has the most uniquely explained variance, and that's the first one we put in the model, then the next one, then the next one, the next one. Hierarchical modeling is pure theory. We're going to use that especially if we are looking for covariates, because we want to control when those covariates enter the model. We're going to definitely use it if we're wanting to look for nonlinear trends, because generally we're wanting to look for the linear trend first and then find out in an additional hierarchical block whether a nonlinear trend occurs. And most likely if we're looking for interactions, because again, we'll want to put those interactions in after we've already accounted for the main effects or the individual effects of the predictors that make up that interaction. Hierarchical modeling will also be used when we're really doing hypothesis testing and we have theoretical and past research reasons to know which variables we should put in first. We can also move forward in looking at basically just trying to create a good predictive model. So this is still based on statistics, but it's a little bit more systematic in trying to find the very best predictive model on this particular sample. And again, those methods include forward regression, backwards regression, and stepwise. So generally speaking, forward regression again is going to add the largest predictor of variance, and that's not necessarily unique variance, just total. Which predictor explains the largest total variance in the outcome? We put that one in first, then it automatically, and again, we're not putting it in, the equations itself, the program is doing this for it. It's doing it all automatically at this point. And it's just then going to look what's the next biggest predictor, etc. And it's going to keep adding them till the first time it adds one and it does not significantly change the overall model of prediction, at which point it's going to stop. Backwards does this the exact reverse. It goes backwards. It adds everything in and then starts pulling out the smallest predictor one at a time as it moves towards the bigger predictor. And the first time it pulls something out that makes the model significantly worse, it stops and puts it back in. And we talked about stepwise, that basically does forward and backward sequentially, trying to find the very best possible fit to the model. Now, we really didn't necessarily talk about this, but we can also get a little bit more advanced, because when we're using hierarchical regression, we're determining in what order the variables are put in, and we're also being able to create blocks of variables. So for instance, we could have a single variable in the very first block. This is what we know in the past has been a very strong predictor. We could then have three confounds or covariates we measured, and we put all three of those in the second block. Now, when we put those three in a second block, we get to choose how they're going to be entered within that block. Do we want them entered forward, backward, stepwise, or enter? And that's why I'm kind of referring to this as a combination of systems. And then again, we could have interactions in the fourth block, nonlinear trends in the third block, and interactions in that fourth block. And again, if there's multiple interactions, how do we want SPSS to choose to look for those interactions? Do we want to do it forward, backwards, or stepwise? Now, the only time we're choosing whether we're using enter method, forward, backwards, or stepwise in blocks within hierarchical modeling is whenever we're actually adding more than one variable at a time in a block. If we are completely creating a brand new block for every variable based on past theory, for example, we have a single predictor in block 1, we have the first covariate in block 2, second covariate in block 3, third covariate in block 4, nonlinear trend of our predictor in block 5, and the interaction between our predictor and one of the covariates in block 6. In that case, we're doing true hierarchical regression. We've completely controlled the order that the program is going to look at those relationships. And again, once we have these multiple models, so whether it is we're doing enter, forward, backward, stepwise, or hierarchical modeling, we are going to get information on the process. It's going to show us how it started. So if it was backwards regression, the very first model would have everything in it. The second model would have one removed. The next model would have two removed, etc., until removing things no longer actually created a change. Or in forward, we would have the first predictor in the first model, two in the second model, and it would continue again until it found a model that did not increase the significance of the prediction, and then it would stop. So to look at these models, we also need to interpret how these models are changing. And what we're looking at again is basically the R square, how much total variance in prediction is being explained by this model, and is that significant, which is the F. So that's what we're looking at each model, but we're also looking at the F change. How much does each model significantly increase in prediction over the last model? Once we have the model chosen that we're going to use for our prediction, then we're looking at those significant t-tests. We're interpreting the individual regression coefficients of the predictors. And once again, this is another time where we can take a look for the possibility of multiclinearity if we didn't initially look for the relationships between all our predictors in a general correlation matrix. And what we're looking for is if our coefficients are wildly changing from model to model. That's often, again, an indication of multiclinearity. For instance, if you have a strong predictor in model 1, it's very weak in model 2, but suddenly it's strong again in model 3, that's giving you an indication that the program, the formulas in the multiple regression are struggling to figure out what to do with these highly multiclinaric variables. So again, just looking at SPSS, at this concept of model comparison, again, we have an example of 3 models that were tested, model 1, model 2, and model 3. And as we're looking at that, so the first thing is the model summary. So this information is giving us that R square, it's giving our degrees of freedom, and it's giving us the significance of the F change. So we can tell as model 1 goes to model 2, goes to model 3, we are getting a higher R squared. So if you look at the adjusted R squared in this top chart, you're going to see, and again, it's not highlighted in red, but just find the adjusted R square column. It's about the 4th one through the table. You're going to see the first model explains 0.28 variance, so about 28%. The second model predicts 31%, and the third model is predicting almost 40% of variance in our predictor, our outcome. So the next thing we're looking at the R squared change. So how much is the R squared changing from model to model? Notice the R squared change initially listed for the first model is 0.31, which is higher than the adjusted R squared of the total model. The adjusted R squared is what we're actually wanting to look at in the model. R squared by itself tends to overestimate. So the R squared that we actually get out of multiple regression is usually an overestimation of how much variance is being explained. And therefore, when we really want to report how much we're actually explaining with the variance, the effect size that we want to use initially is that adjusted R squared. However, the R squared change is based on the unadjusted R squared change. So again, R squared change in this case, the first model, there is no change. It's 31% of variance explained. So the non-adjusted R squared. As we go to model 2, we're increasing 0.05. So about 5% of variance is being further explained by that next model. Model 3 is adding almost 10% of the variance explained. Next thing we're looking at is the F change. So again, how significant is this model at prediction? Now notice that again, the F change is showing how much the F is changing from model to model. But what we're really interested in is the significance of the F change. So for example, notice that when we go to model 2, it actually is not a significant increase in prediction. The significance value, the significance of F change is 0.159, or basically 0.16. So we have a P of 0.16, above 0.05. But in this case, model 3 actually finds that we do have a significant increase over model 1. So model 2 would be thrown out, but model 3 is something we want to use. So most likely this was actually either being done through a hierarchical regression where we forced SPSS to make the multiple regression look at all 3 of these models, or this would have likely have been a stepwise regression. Because if it had been simply enter, model 1 would have been tested, model 2 would have been tested, found to be not significantly better, and it would have stopped. And that's a good illustration again of why we have to be very careful what type of multiple regression we're using, because different types will give us different results. Then we look at the coefficient. So we know model 3 is the one that we want to use. It's the significant improvement. It explains more variance. So now our question is, what are the significant predictors within model 3? And that's where we're going to go to this bottom chart, where we're actually going to interpret both the regression equation, so what is the constants for this regression equation, the slopes, so what is the increase or decrease in our predictor for every one level of depression, anxiety, and sex. And this is the unstandardized B, that second column on the bottom chart. We then actually want to look at the actual, whether it's significant or not. And again, notice in this case that the overall model, actually depression is not significant. So the regression coefficient for depression is a T of negative 1.167 and the significance of 0.25, above 0.05. So actually the 2 predictors that are actually significant in this model are anxiety and sex. Depression actually is removed at this point. Now, notice that depression was a significant predictor in the first model, it was a significant predictor in the second model, and now it's no longer a significant predictor once we add anxiety. That isn't a guarantee of multiclinearity, but it probably does mean, as we well know, that depression and anxiety often are somewhat related to each other. The final thing this actually tells us, if we have a better understanding of multiple regression, is that because there is a non-significant predictor in Model 3, we now know this wasn't a stepwise regression. This had to have been a hierarchical regression. We told SPSS what we wanted in Model 3, and we told it to put all three of these in. And that's why just looking at whether the model is significant is not necessarily enough. We also then need to look at the model's coefficients to find out within that model what are the significant predictors.